Hi, I'm Yue. I'm presenting the paper Associative Transformer is a sparse representation learner. Inductive biases, like convolution operations in the convolutional neural network, is important for guiding the model to generalize effectively within the underlying data distribution. Unlike the convolutional neural networks, transformer models employ the pairwise attention without inductive biases aligned with the input data structure, which makes them less effective when handling the new or unseen samples. Transformer models designated bottleneck for localized and contextual representation learning. Our proposed approach aims to leverage the computation among input patches to naturally drive the spatialized pairs, contributing to the sparse association of information and reducing the computational burden of the architecture. We first explore the existence of computation within the transformer models of attention and its impact on the different modalities. Our analysis of the attention heads in both the Gaussian transformer and the BERT transformer models shows that there's a varying sparsity with usually the middle layer exhibiting a notable degree of sparsity compared to the lower and higher layers. We show that the computation among attention heads in pairwise attention proves to be crucial for learning meaningful representations on viewing the naturally sparser interactions that enhance the overall learning process. This work is inspired by the global workspace theory. The modularization of knowledge can find the resonance with the neuroscientific grounding of the global workspace theory. It explains a cognitive architecture where diverse spatialized modules compete to write the information into shared workspace through a communication bottleneck. The global workspace theory involves the guided attention within a limited capacity workspace, and the modules try to compete with each other, and the information entering the space will get the availability through the broadcast to the other modules in the system. An exemplary approach for implementing the global workspace is the coordination method, wherein the cross attention is employed to selectively activate the patches from the input sample. This method comprises two steps, the writing step and the broadcast step, both intricately based on the cross attention mechanisms. And our approach tries to improve this architecture by implementing the associative memory and a more efficient global workspace. The global workspace enables an efficient information writing and reading by learning a set of pairs in explicit memory. The inductive biases through the pair spatialization is based on three steps. First, it collects the patches from all the batch samples, and secondly, computing the bottleneck attention and selecting patches. And thirdly, the information is broadcast from the global workspace. First, the squash layer in the first step try to concatenate all the patches from different samples within one batch, so we can have a diverse selection of different patches. Then the squash representation are projected to a low-rank latent space of dimension and sparsely selected and stored in the explicit memory, while the fixed bottleneck. The bottleneck attention is based on the multi-head cross attention, allowing only a few of the patches to enter the workspace, which is the explicit memory in the architecture here. introducing the computation among different patches. The explicit memory stores and updates a set of pairs by attending to different patches, which are then smoothed by the exponential moving average method. We also included the balance loops to encourage the diverse selection of the different patches. We will show a few examples of the effectiveness of the list loops. In the second step, the explicit memory is updated. Then, following that, the whole field network try to use the lended pairs in the memory as different attractors to reconstruct the current input patches. In this graph, the LT represents a learnable linear transformation, which is used to scale the memory content to match the current input dimension, since the memory is the low-rank memory. Iteratively decreasing the energy of a patch with respect to these different attractors enables the effective retrieval of knowledge within the explicit memory. Here I show different graphs related to the whole field network. In the upper graph, the global energy over the batch time steps, we can see it's a generally decrease with the batch time step. In the lower graphs, we demonstrate that the inverse temperature beta is a very important hyperparameter here that influence the formation of metastable states. A metastable state is a representation that encompasses multiple patch representations. A smaller beta is more likely to generate such metastable states, where a larger beta leads to a stronger separation of different patterns, as shown in the graph on the left-hand side. However, we have shown that if the beta is too large in the associative transformer, it can also lead to a local minimum, where the input patterns are reconstructed to the same pattern within the associative transformer as shown in the graph on the right-hand side. We then call this associative memory augmented attention layer, the global workspace layer, and the architecture is called the associative transformer block. This layer can be viewed as an additional component integrated in the traditional vision transformer block. Presented here are the lended bottleneck attention maps based on the Sifferton dataset. On the left, I provide a glimpse of the attention maps using 4 distinct pairs from 4 individual input images. As observed, patches across samples are attended to sparsely by different pairs. Moreover, I showcase the complete 32 pairs in the memory bank, emphasizing the emergence of the spatialization. Here are examples of the selected image patches by the bottleneck attention. We can observe a noticeable increase in the sparsity and the diversity of different selected patches with the progress of the training. The image classification tasks were employed to evaluate AIT's performance. AIT outperforms other latent memory-based transformer models, including the coordination and the perceiver methods, with a smaller or comparable model size. AIT is also a layer-efficient model. Compared to VIT-based, the AIT median is a shallow model with only 6 layers. However, AIT median can exhibit an average performance much better than the VIT base. At the same time, requires only much fairer parameters. The sort of clever dataset presents a multimodal reasoning task involving both image and text question inputs. In addressing relational reasoning tasks, AIT achieved a competitive performance with other non-transformer-based models, which are relying on a built-in inductive biases. It shows that the AIT can indeed use the proposed framework to facilitate the efficient association among disparate information fragments. To summary, we introduced the Associative Transformer, AIT, a biologically plausible learning framework based on the global workspace theory and associative memory. The AIT functions as a sparse representation learner, utilizing the bottleneck attention to acquire specialized powers. Adaptively, adaptive low-rank powers increase the memory capacity, allowing the AIT to learn up to 128 specialized powers. We recommend refer to the paper for more details. And finally, the learned powers can serve as attractors in whole-field network, which is the first work to incorporate the whole-field network as the integrate elements in a sparse attention mechanisms for inductive biases.